Okay, let's jump right in. We're doing a deep dive today into the source material you shared, all about how stars move right here in our own galactic neighborhood.
Yeah, and we're really zeroing in on one specific kind of fascinating feature in all that motion,
Yeah.
the Hercules stream. It's quite prominent.
Right, and the sources you've pulled together give us this great historical sweep, don't they? From, the earliest ideas right up to the latest stuff from Gaia.
Absolutely. Hipparcos was big, but Gaia, well, Gaia's just been a total game changer for this field.
So our mission here is to unpack all that. Follow the story of how we figured out what's going on with structures like Hercules.
Exactly. Peel back the layers, look at the data, the theories,
Yeah.
see where we stand now.
Okay, so where does the story start? Historically, I mean.
Well, way back, people like William Herschel, they sort of assumed stellar motions were basically random, just stars zipping about on their own.
No particular pattern.
Not really. That was the initial thought. But then, early 20th century, Jacobus Kapteyn notices something. He finds that, actually, stars do seem to have preferred directions of motion. Not totally random. He identified two main streams. Kind of.
Ah, and those turned out to be linked to known groups.
Yeah, later identified with what we now call the Hyads and Ursa Major streams. So right there, the idea of pure randomness starts to fray a bit.
And then things get more complicated.
Much more complicated. This is where Olin Egan comes in. He did decades of work, mainly before the big space missions like Hipparcos.
Working with ground-based observations.
Right. And he didn't just see two streams. He identified a whole bunch of what he called kinematic groups.
Kinematic groups, moving groups, dynamical streams, superclusters. They had a few names, right?
Exactly. And the key thing was these groups seemed to be collections of often older stars that weren't just going around the galaxy in nice, simple circles like most stars in the disk.
They had these shared sort of bulk motions that were different, higher peculiar velocity.
Precisely. They stood out from the general flow. And your sources list some key ones Egan found.
Like the Hyades supercluster. Egan's stream, oh, about 600 million years old.
Yep. And the Ursa Major group, or Sirius Supercluster Stream 2, maybe 300 million years old.
And younger ones, too. Pleiades moving group.
Right, the local association, only 20 to 150 million years old, plus IC 2391, Castor. He built up quite a catalog.
So what did Egan think these groups were?
Well, his first thought was pretty logical. Maybe they're just the remnants of old open star clusters that have gradually dispersed over time.
Like the cluster stars drift apart but kind of keep moving together for a while.
Sort of, yeah. And we do think that's true for some younger moving groups. They really are evaporation trails from clusters.
But not all of them.
That's the thing. Over the last, say, 20 or 30 years, the picture's gotten bigger. Many of these groups, especially the older, more spread out ones, they might not just be from dissolving clusters.
So something else is creating them, or organizing them.
Exactly. The idea grew that maybe global dynamics are at play. Resonances. The gravitational influence of the whole galaxy structure, like the central bar, the spiral arms, these massive features could be shaming these streams.
Ah, okay. But back in Egan's time, that was harder to prove, right? Because of distances.
That was the big challenge. You need really accurate distances to get the full 3D space velocity and confirm if a group is truly moving together in space or just looks like it from here. Egan often had to infer distances, which left room for doubt, especially for those older streams.
So enter the space telescopes, Hipparcos first.
Yes, Hipparcos, with its data from 1997 onwards. That was a huge leap.
Yeah.
Suddenly we had much better distances, much better velocities for thousands of stars. It allowed for real quantitative checks.
And it confirmed Egan wasn't just seeing things. These streams were real.
Pretty much, yeah. It solidified the reality of many of these streams, even older ones. The sources mentioned some key Hipparcos results.
Like finding streams in the halo. Debris from eaten galaxies.
Right, Helmy et al. Found a cold stream they linked to an accreted satellite. And Navarro et al. Argued Egan's old Arcturus group was probably debris from another merger event, maybe 5 to 8 billion years ago.
But importantly for us, Hipparcos also confirmed streams closer to home in the thin disk.
Absolutely. Danon, in '98, used Hipparcos data, found clear evidence for Sirius Ursa Major, Pleiades Hyades, and crucially for the Hercules stream.
Okay, so Hipparcos puts Hercules firmly on the map. But Gaia was another level entirely.
Oh, completely different scale. Before Gaia, Maybe we knew about 100 stars likely belonging to Hercules.
And now?
Now, with Gaia DR2 and DR3, we're talking tens of thousands of stars in that velocity region, all with incredibly precise measurements, positions, motions, distances. It's transformed our ability to see the structure.
So let's focus on Hercules then with this Gaia power. What defines it? What does it do?
Well, it's a very prominent group near us,
Mm-hmm.
and its main signature is its motion relative to the sun and the average stars. It kind of lags behind the general galactic rotation.
So it's orbiting slower than us.
Slower in terms of rotation, yeah. And it also tends to be moving outwards, radially, in the disk.
Okay, lagging and moving outwards, and the explanation involves these resonances.
That's the main idea, yes. You have these big non-axisymmetric patterns in the galaxy, the bar, the spiral arms rotating. Stars orbiting near them can get into these dynamical locks, these resonances, where their orbital frequencies sync up with the pattern's rotation in specific ways.
Right. And the sources mention three key types. Corrotation.
Yeah, corrotation is where the star's orbital speed basically matches the pattern speed, so the star kind of stays put relative to the bar or spiral arm it's near.
Okay. Then the inner Lindblad resonance, ILR.
That's closer in. The star orbits faster than the pattern. The ILR happens when the star's natural wobble frequency, its epicyclic frequency, syncs up with how often it gets overtaken by the pattern. It gets a repeated gravitational kick.
And the outer Lindblad resonance, OLR.
That's further out, where the star orbits slower than the pattern. The pattern keeps overtaking the star. Again, it's a specific frequency match that leads to repeated kicks, changing the orbit.
Got it. So early models tried to link Hercules to one of these. You mentioned Danin's 2000 paper.
Right. Using a simplified model of just a bar potential, he found that stars trapped in the bar's 2.1 OLR, a specific outer Lindblad resonance, could create a moving group with properties like the Hercules stream.
But there was a catch.
A pretty big one, yeah. To make his model match the Hercules data available then, he needed the bar to be rotating quite fast, about 53 plus or minus 3 kilometers per second per kiloparsec. That's generally considered on the fast side for a galactic bar.
Okay, so fastbar, 2.1 OLR model.
Yeah.
Then comes Gaia DR2 in 2018.
And boom, people like Katz et al. Map the velocities near us with this incredible new precision, and they look at the Hercules region, and it's not just one lump.
What did they see?
They saw a clear trimodal structure, 3 distinct peaks, 3 substreams basically, clustered around roughly 220, 280 kilometers in rotational velocity.
Wow. 3 streams hidden inside the one.
Yeah. Hercules 1, 2, and 3, they're sometimes called. And that slowest one, Hercules 3. Turns out it matches Egan's old HR 1614 group almost perfectly.
That's amazing. A connection right back to Egan's early work.
It really is. But finding this trimodal structure immediately complicated things. A single resonance from a simple bar model. It didn't easily explain 3 distinct peaks like that.
And lots of other researchers confirmed this finding quickly.
Oh yeah, the sources list quite a few. Minari, Hunt and Bovey, Ramos, Frag, Cudi. Many teams saw this clear structure in the Gaia data. But then another complication arose.
The bar speed again.
The bar speed again. While the fast bar model for Hercules was being questioned for the trimodal structure, other groups were using the same Gaia data to measure the bar's pattern speed independently. And they were getting slower speeds.
How much slower?
Numbers more like 35 to 41 kilometers kpc. People like Chiba, Clark, Sanders, Bovey. They were finding results inconsistent with that fast 53 kilometers kpc needed for the original Denon model.
Okay, so the structure is more complex than we thought, and the likely speed of the bar doesn't fit the old explanation. What now?
Well, this led to a whole flurry of alternative ideas. Everyone still agreed it was likely resonances from the bar or spirals doing this, but which resonances and how became the big question, especially if the bar is slow.
So what were some of these alternative theories?
Well, Perez Villegas and others suggested maybe it's stars orbiting the bar's Lagrange points, special points of gravitational balance.
Okay.
Hunter Bovey proposed it could be a higher order resonance of a slow bar, specifically the 4.1 OLR.
Different frequency match.
Right. Minari and collaborators suggested a mix, maybe corrotation, and the 6.1 OLR.
And spiral arms came into play too?
Yep. Mikshenko et al. Pointed towards an inner Lindblad resonance, the 8.1 ILR, but caused by the spiral arms, not the bar.
And Hattori et al. Looked at the combined effect of a slow bar plus spirals, suggesting a 5.1 ILR could be involved. So lots of possibilities, mostly involving a slow bar or spirals or both. How do you sort through all these competing ideas?
That's where big computer simulations come in. N-body simulations. The sources highlight work by Asano et al. In 2020. They used a really sophisticated simulation of the Milky Way, the Fuji model.
billions of particles, simulating cosmic history.
Yeah, 5.1 billion particles evolved over 10 billion years. It simulates the gravity, the star formation, the whole shebang, and they let a bar and spirals form naturally within the simulation.
And what did their simulated Hercules stream look like?
Well, when they looked at the stars in the solar neighborhood region of their simulation, they found the Hercules structure was dominated by stars caught in multiple resonances, primarily the 4.1 and 5.1 OLRs and the corrotation resonance of their simulated slow bar.
And did that match the real Gaia data, the three peaks?
It did remarkably well. This combination naturally produced the trimodal structure, and it accounted for a significant chunk of stars. Crucially, this happened with a slow bar in their simulation, around 40-45 kilometers kpc.
Ah, so the simulation strongly favored the slow bar multi-resonance picture.
It seems that way, yeah. Yeah. And they also noted that other resonances in their sim, like the 2.1 and 3.1 ORs, matched other, fainter structures seen in the Gaia data near Hercules, features sometimes called the hat and the horn.
Okay, so simulations are pointing towards a slow bar and multiple resonances. Is that the final word?
Almost. There's one more recent twist, coming from the even newer Gaia DR3 data.
Oh, what now?
Well, work by Chiba et al. Again, in 2021, analyzing the very subtle kinematics in DR3. They found evidence that the bar might not just be rotating slowly, it might actually be slowing down, decelerating over time.
The bar is hitting the brakes. Why?
The likely culprit is dynamical friction. The bar is rotating within the massive dark matter halo surrounding the Milky Way. This halo isn't perfectly smooth, and its gravity effectively drags on the bar, causing it to lose angular momentum and slow down.
Okay. How does a slowing bar explain Hercules?
It's quite elegant, actually. If the bar is slowing down, its resonances, the OLRs, corrotation ILRs, aren't fixed in place. They slowly sweep outwards through the disk's phase space.
Ah, they move.
They move. And as a resonance sweeps across a region, it can capture stars that weren't previously resonant. Because different resonances sweep at slightly different rates and affect stars with different initial orbits, this sweeping and capturing process can naturally build up multiple distinct streams, like the trimodal Hercules structure over time.
So the complexity we see is a result of this dynamic sweeping process.
That's the current leading idea, yeah. It fits the detailed structure observed in Gaia DR3 very well. They even estimated the rate of slowing.
What did they find?
About minus 4.5 kilometers per second per kiloparsec per billion years. The minus sign means it's decelerating. It's a slow process, but over cosmic time, it has a big effect.
Wow. Okay, so let's recap this journey. We started with Herschel thinking it's all random.
Then Kapteyn sees hints of order. Egan meticulously maps out numerous moving groups, suspecting cluster origins.
Hipparcos confirms the reality of these streams and gives us better data.
And then Gaia arrives, revealing this incredible, complex trimodal structure within Hercules, challenging simple models.
Leading to debates about bar speed, multiple resonances from slow bars or spirals.
Supported by massive simulations, and finally culminating in this idea of a decelerating bar whose sweeping resonances sculpt the streams we see today.
It's amazing how each new data set hasn't just refined the picture, but fundamentally changed our understanding of the dynamics involved.
Absolutely. It shows these streams aren't just static features, they're active tracers of the galaxy's evolution, shaped by these huge underlying structures like the bar.
You have to think Olin Egan would be absolutely fascinated by where his initial discoveries have led with the kind of data we have now.
Oh, definitely. It's a fantastic example of building on previous work. His meticulous cataloging laid the groundwork, even if the interpretation has evolved dramatically.
And understanding Hercules ultimately isn't just about Hercules, is it? It tells us about the Milky Way itself.
Precisely. It's a key piece of evidence for understanding the properties of the bar, its speed, its evolution, its influence, and how these large-scale structures shape the orbits of stars like our own sun throughout the disk.
So, wrapping this deep dive up, what's the final thought to leave us with?
I think it's the realization that studying the incredibly precise, almost subtle movements of stars right here in our own corner of the galaxy, well, it allows us to diagnose the behavior of these immense, powerful, invisible structures like the bar and the dark matter halo that dominate the entire Milky Way.
It's like local symptoms revealing a system-wide condition.
Exactly. So maybe consider this. How the detailed patterns in stellar velocities near the sun act almost like seismic waves, letting us probe the deep, evolving structure and history of our galactic home, a history stretching back billions of years, all revealed by tracking tiny points of light.